Good day, welcome back for the fifth and final part of our discussion on trig substitutions. In this video, I want to go through one final example together and then summarize the associated class worksheet I mentioned at the end of the previous video. So if you haven't taken the time to locate the class worksheet and work through some of the problems, I would encourage you to do so before going too much further in this video. Remember, one of the best ways to learn mathematics is to sit down and spend some time working on it on your own. And I know we don't always like to hear it, but sometimes we really have to struggle through it a bit to understand these ideas that are involved. For this first example, if we were to encounter this example in a sitting outside of specifically discussing trig substitutions, maybe on an exam or a homework assignment where we simply say evaluate the following integrals, we will need to determine kind of how we are going to approach the problem. So let's just go through our thought process. This really doesn't look like one of our standard forms for integration by parts. I don't see one of these expressions we've been discussing related to trig substitutions, and it's not a trig integral. So could I possibly do a substitution? And we've encountered a few examples similar to this in the past. Thinking about it from a substitution perspective, could you pause the video and just recommend a generic substitution that would help you evaluate this integral? Thinking about this from a very intuitive perspective, I would want to try to get this x dx to essentially play the role of my du. So there's no guarantee of that being exactly du, but what u would I have to pick to choose that? So if du was going to be x dx, you would tell me that u needs to be 1/2 x squared. And that 1/2 is somewhat inconvenient. So how about instead we say u is x squared, which would force du to be 2x dx. So the x dx in our integral, we would want to make that 1/2 du. So in terms of this substitution, x to the 4th is really x squared squared. So just rewriting this, we can have this as the square root of 1 minus x squared squared x dx. And now we very clearly can get everything solely in terms of u. The 1/2 is a constant which pulls out front. And what we're left with is the square root of 1 minus u squared. So at this point, we've just reasoned our way through this using the mental approach we've developed. The only possible technique we can think of to apply here is a substitution, and based upon the x dx, a reasonable substitution seems to be x squared. Now that we've made this substitution, we have a very reasonable integral remaining, at least in terms of our current discussion on trig substitutions. Now we can use the trig substitution u equals sine of theta. And we've already evaluated this exact integral if you go back to the second example on the part 1 video for this section. So I'm not going to go through all of the details. I'm going to put a ... but I would encourage you to make sure that you can finish it up and compare to that solution you had on the initial video or the first page of your note sheet. And once again, kind of a takeaway or a bigger picture observation is that when it comes to evaluating indefinite integrals, it is perfectly reasonable to use multiple techniques of integration in the same problem. You may have to do a substitution in order to get it into a form where you can do a trig substitution. So keep that in mind. And I'd like to finish up this discussion by going over at least portions of problems 2A and B from that class worksheet. And note the class worksheet, it only has 3 integrals on there for you to evaluate. So really, if you haven't taken the time to do so, this would be a great opportunity to get in some good solid practice. So immediately looking at this first integral based upon the form, the square root of 4 minus x squared, this is an ideal scenario for a trig substitution. In fact, I don't see any other approach that we could use, at least to get started here. Because of that 4 minus x squared, we're going to use the substitution x equals 2 sine theta, which forces dx to be 2 cosine theta. So rewriting everything now in terms of thetas. Underneath the square root, we have 4 minus 4 sine squared of theta. The x squared in the denominator is 4 sine squared of theta. And dx is 2 cosine of theta. And hopefully at this point, from doing substantial practice, we are getting quicker and more efficient with the typical simplifications. So underneath this square root, we have the quantity 4 times 1 minus sine squared theta. So you could simplify what's underneath this square root to be 4 cosine squared of theta. And just to walk our way through it in words, the square root of that would be 2 cosine theta. So in the numerator you have 2 times 2, and the bottom you have 4. Those cancel. You have a cosine squared in the top, a sine squared in the bottom. So I'm going to let you do 1 or 2 simplification steps, but what this results in is the trig integral cotangent squared. And this is the reason I wanted to say a bit about this example, because I don't believe we've integrated cotangent squared, at least together in one of these videos. But we have antidifferentiated tangent squared multiple times. And remember, when we antidifferentiated tangent squared, we did so by rewriting it with its Pythagorean identity. And that technique worked extremely well. And if we've seen something similar be evaluated in a certain way, that's a good indication that we should try that approach here as well. So let's kind of do a little bit of work to the side thinking of the Pythagorean identities. So we typically think of cosine squared plus sine squared equals 1. And there's really 3 key Pythagorean identities. We can divide each and every term by cosine squared to get the one involving secants and tangents, or you could divide each and every term by sine squared, and in this case you get a third equivalent version of the Pythagorean identity, which is that cotangent squared plus 1 is equal to cosecant squared. So cotangent squared is cosecant squared minus 1. In order to antidifferentiate this cotangent squared, we will rewrite it as cosecant squared minus 1. And here we have really followed almost precisely step by step exactly how we would integrate tangent squared. All that remains is taking care of these indefinite integrals. And let's just kind of recall, if you wanted to differentiate cotangent of theta, the derivative of cotangent is minus cosecant squared. And if we turn that around for an antiderivative, the antiderivative of cosecant squared is going to be minus cotangent theta plus c. So using this fact, which is just a common differentiation, and I guess hence a common antidifferentiation formula, even though it's not something we use all that frequently, we have minus cotangent theta minus theta plus c. And we've now certainly taken care of the most difficult portion of this problem. To finish it up, let's go ahead and look at our substitution above and draw that associated triangle. X over 2 is sine of theta. We have this right triangle. Sine of theta is opposite over hypotenuse. And by the Pythagorean theorem, the length of that bottom leg is the square root of 4 minus x squared. Furthermore, note if we want to get just a theta, we really need to evaluate the inverse sine of both sides. So we have minus cotangent, and cotangent is going to be adjacent over opposite, minus theta, which is arc sine of x over 2, all plus c. And something that's worth giving occasional reminders of is that this is essentially what your work should look like, except you should fill in those details, on homework assignments and exams. A single vertical column using good mathematical notation and including all of this relevant side work to the side. Now, note, I'm perfectly fine without you including these reminder details, but the substitution, the right triangle, those all certainly need to be included. For problem 2b on the worksheet, I don't want to go through all of the details. I just want to help you out with the initial algebra step. Looking at this integral, specifically focusing in on this x squared minus 6x plus 13. This is extremely similar to an example from our previous video. If we could complete the square, we would be in an ideal scenario to perform a trig substitution. And I realize that completing the square is not always our favorite algebraic thing to do, but it is a technique that we are going to encounter multiple times throughout the semester. So this is time well spent to help us out later on. So let's look at this quantity. X squared minus 6x plus 13. How I want to think of writing this is x minus something squared plus a number. So if I have x squared minus 6x, that would be the first two terms of x minus what number squared? 3. And note, how do we go from that minus 6 to 3? We simply divide that coefficient of x by 2. And if you were to write out all of the terms for x minus 3 quantity squared, it would be x squared minus 6x plus 9. And if we want a plus 9, we either have to borrow it from the 13 or just write plus 9 minus 9. Minus 9 plus 13 leaves a plus 4 left over. So by completing the square, we now have a, I think, much more reasonable looking integral. And we can evaluate this using a trig substitution. The substitution that I would recommend is to let x minus 3 equal 2 tangent of theta. And from here, I will let you finish up the problem. But I will note, as usual, you can find full solutions located on Canvas. So make sure that you're spending some time to finish up this worksheet, check your solutions, and work suggested problems. When you have questions, do not hesitate to reach out. So stay tuned and take care.